The first problem you can see, I suppose, what are the two components of iron losses and what are they dependent upon? So we know hysteresis loss and eddy current loss. We had discussed about this in the class. So the next portion of the problem is the total core losses of a ferromagnetic specimen is found to be 1500 watts at 50 Hertz and 3000 watts at 75 Hertz when the flux density is kept constant, because hysteresis loss as well as eddy current loss will heavily depend upon what is the kind of flux you are seeing in the ferromagnetic core. Calculate the two components of iron losses separately for each of these frequencies. So let's try to do this. So this is tutorial sheet number 10. Okay, and we are trying to do problem 1. So what it says is core losses, that is consisting of hysteresis loss plus eddy current loss. Both of them added together is 1500 watts at 50 Hertz and 3000 watts at 75 Hertz. Now, what is being asked is find out each component at both these frequencies. So we are supposed to find out what is the eddy current loss and what is the hysteresis loss at every frequency. So I think when we discussed in the class last time, we said that hysteresis loss is proportional to frequency, because we said that it is area under the BH loop, which is actually the area under the BH loop is, if I try to calculate whatever is the area multiplied by x-axis scale and y-axis scale, it will give me what is the loss per cycle and per unit volume. Okay, so if I multiply that by frequency, I'll get what is watts per second for unit volume. Okay, watts per unit volume. So it is proportional to frequency. So I would say area under BH loop multiplied by frequency multiplied by volume will give me the hysteresis loss. So this will be hysteresis loss in watts, okay, for the entire specimen. Okay, if I multiply by the volume also, it's going to give me the complete hysteresis loss in watts. So the bottom line is the hysteresis loss is proportional to frequency. Whereas if I try to look at eddy current loss is because of the I square R that is happening within the specimen of the core. Okay, so in which case I'm going to have whatever is the induced EMF E. If I say induced EMF is E in the iron core. So that is actually going to be proportional to d phi divided by dt. So in which case I should say E divided by R is going to give me I, which is the eddy current. So I should say if I am talking about eddy current losses, I square R, that is going to be the eddy current loss. So which means that is going to be proportional to either phi square and also I should say frequency square, because 1 by T is indirectly the frequency. So I should say this becomes proportional to both frequency square as well as phi square in one sense. Okay. So if I assume that flux density is a constant that is not changing. As per the problem statement, B is not changing. Flux density is remaining as a constant. So which means flux is remaining as a constant. This is not going to vary. If this does not vary, I should say loss at 50 Hertz. If I try to calculate, I should say hysteresis loss, which is proportional to frequency, and I should say eddy current loss, which is proportional to frequency square. So I can write this as sum A times F plus sum B, or let me write A1 and A2. That's easier. So let me write this as A1 times F plus A2 times F square. Okay. The same way that is equal to actually according to this 1500 watts. And similarly, I should be able to say A1 times F, which is actually 75 in the case of 75 Hertz, and A2 times 75 square is going to be 3000 watts. So here I can say 50 times A1 plus 2500 times A2 will be equal to 1500 watts, whereas I have to write 75 A1 plus 75 times 75. So that is 5675. A2 should be equal to 3000. So if you solve for what is A1 and A2, I should be able to express very clearly what is the hysteresis loss component and what is the eddy current loss component. Okay, so I can write hysteresis loss at 50 Hertz. So if you solve for this, I think A1 and A2 is coming out to be 0.4 and A1 is coming out to be 10. Check it out. This is what we are getting when we solve for. Okay. So hysteresis loss at 50 Hertz happens to be A1 10 times 50. So which will be 500 watts. And similarly, hysteresis loss at 75 Hertz, if I try to calculate, it will be 10 multiplied by 75, which is 750 watts. So I should be able to calculate again eddy current loss at 50 Hertz. That will be 10 multiplied by, 75 Hertz. 10 multiplied by 50 square, 0.4 multiplied by 50 square. Eddy current loss, if I have to calculate, I should say 0.4 multiplied by 50 square. Right? So that will be 1000 watts. And if I try to do the other one, which is eddy current loss at 75 Hertz. At 75 Hertz. So that is going to be 0.4 multiplied by 75 square. Okay. And I think that will come out to be 2250 watts. So we have got the components which are hysteresis loss at 50 Hertz and again hysteresis loss at 75 Hertz. And similarly, eddy current loss at 50 Hertz and eddy current loss at 75 Hertz. Okay? Is that all right? Any questions? Is this clear? So the next one. So the next question, the statement is as follows. A toroidal core with a mean diameter of 10 centimeter has a rectangular cross section with 3 centimeter width and 2 centimeter depth. Its BH curve can be approximated by 2 straight lines like this. Whatever is shown here, that is essentially the BH curve. So what is being asked is, toroid is wound with 125 turns. Determine the inductance of the coil and the maximum value of current if the flux density in any part of the core is below 1 Tesla. And the same way, determine the minimum value of current for which the complete core has a flux density of 1 Tesla or greater. Please remember, if you look at this particular graph, 1 Tesla is exactly the point at which it is transitioning from this kind of characteristics to this kind of characteristic. The slopes are different in two portions. Below 1 Tesla and above 1 Tesla, you are having two different slopes. Okay. So let us try to do this. So this problem number 2. The statement is somewhat like this. It is a toroidal core. So toroid is something like a ring. So you are having a ring like this and it is wound with 125 turns. So this is having 125 turns. Okay. And what is being told is this toroid has a rectangular cross section. So if I cut it here, it will have a rectangular cross section. And the rectangular cross section has 3 centimeter by 2 centimeter area. The cross sectional area is 3 by 2. So I can write this as 3 by 2 centimeter square. This is the cross sectional area. And the dia is given to be the mean diameter, rather, that is given to be 10 centimeter. That is what is given as the mean diameter. So I should say, first of all, length of the magnetic circuit L will be pi d, right? Because the circumference of that ring, that is what is the mean length of the magnetic field line. So I should say this is pi d. So I should be able to write this as 22 by 7 multiplied by 10 multiplied by 10 power minus 2 meters. Okay, so this is going to be the length of the magnetic circuit. So this is the length of the magnetic circuit in meters. Now, if I try to look at what is the area of cross section, we can write this as 6 multiplied by 10 power minus 4 meter square. Right. Now, let us try to look at this problem once again. It says that determine the inductance of the coil and the maximum value of current if the flux density in any part of the core is below 1 Tesla. So whenever the flux density is below 1 Tesla, I am having essentially this H as 100 ampere per meter. That is the maximum H value that I can have. So I can write again that for 1 Tesla of flux density, maximum H equal to 100 ampere per meter. This is what is given. So you should be able to calculate corresponding to this what is the value of mu. So I can say B divided by H will give me what is mu. So that will be 1 divided by 100 directly. So this is going to be the mu value, which is Weber per ampere or Weber meter per ampere, which also we said Henry per meter or something like that, right? So this is Weber per meter square and ampere per meter, right? This is Weber per meter square divided by ampere per meter. So that will give me Weber per ampere and meter. This is the unit, okay, which is same as Henry per meter. So this is same as Henry per meter. Okay, so this is 10 power minus 2. Now, what is being asked is what is the current? What is the maximum value of current at which the flux density will be 1 Tesla? How would you go about doing this? You got the mu value. From mu, can we get inductance? How do you get inductance? You remember the relationship we wrote? L equal to L, rather if I say L di by dt is equal to N d phi by dt. From which we wrote L equal to N d phi by di. Or I can write this as N phi divided by I. If I say linear relationship, then I can say N phi by I. And if I just multiply this by N and multiply this by N, this gives me MMF. And this gives me flux. Right? So MMF divided by flux is reluctance. So I can write this as N square divided by reluctance. So N square divided by reluctance will directly give me what is inductance value. Okay, fine. Is this clear? So in which case, if I have mu value with me, I can say L divided by mu A. This will give me what is the reluctance at this particular mu value. So I should be able to write this as L we wrote already, which is 22 by 7 multiplied by 10 multiplied by 10 power minus 2, which is actually 0.1, right? We have to write 0.1 multiplied by 22 by 7. So I can write this as L equal to approximately 0.1 multiplied by pi, which I can write this as 0.3314, whatever, right? So this is the length in meters. And area we wrote as 6 multiplied by 10 power minus 4 meter square. And mu already we wrote as, what did we write here? 1 by 100, which is 10 power minus 2, right? Mu is 1 by 100. So I can write this as 1 divided by 100. I should be able to write reluctance in this particular case, that is equal to L, which is 0.314 multiplied by 100 divided by 6 multiplied by 10 power minus 4. So you can calculate what the reluctance is. The reluctance will be ampere per Weber. What we get will be ampere per Weber. So you can calculate what this value is. Once you calculate that value, I can say L equal to N square divided by this reluctance. N is 125 turns. So 125 square divided by this reluctance value. That will give me what is the inductance value. Any questions on this? Is this clear? Inductance is N square by reluctance. You understand the derivation, right? Any questions? Now, if you have this with you, right, we should be able to calculate once you have H value, which is, what was the H value? H value was 100 ampere per meter for this 1 Tesla. If I want 1 Tesla flux density, the H value has to be 100 ampere per meter. Now to calculate the current, I can use this information. So 1 Tesla flux density or under 1 Tesla. Under 1 Tesla flux density will be maintained maintained for a maximum H value of 100 ampere per meter. Okay. So in which case I can say 100 ampere per meter multiplied by the length of the magnetic circuit will give me how much is the MMF. This is the total MMF. What will maintain a flux density slightly under 1 Tesla. Okay. So in which case I should be able to write this as 100 multiplied by 0.314. So I'm going to have 31.4 as the MMF value. So from which I should be able to calculate the current that is needed to establish this much amount of flux density. That will be 31.4 divided by 125 turns. So that is going to give me the current in ampere. Okay. So if I want to maintain a flux density of just under 1 Tesla, this is the way it is. If I want to maintain the flux density slightly above 1 Tesla, going back to this graph, this is the portion that we are talking about. So you can repeat the same thing corresponding to the second portion of the graph. Right? You guys can complete it. Any questions on this? Any questions? Okay. Let's try to look at the next problem. So this problem statement goes as follows. A single phase transformer has 400 primary and 100 secondary turns. The net cross-sectional area of the core is 60 centimeters square. The primary winding be connected to a 50 Hz supply at 500 volts. Calculate the peak value of flux density in the core, voltage induced in the secondary winding. These are the two things that are being asked. So this is 400 by 1000. So let me try to do this problem. So the turns ratio that is given is 400 divided by 1000. That is what is given. And it is written that net cross-sectional area of the core is 60 centimeters square. So I can write cross-sectional area of the core is 60 multiplied by 10 power 4 meter square. Okay. The next thing that is given is if the primary winding is connected to 50 Hz supply at 500 volts. So the primary voltage is given to be 500 volts at 50 Hz. Okay, so this is what is done to the primary. So the first thing that is being asked is calculate the peak value of flux density in the core and voltage induced in the secondary winding. So please recall what we derived as the EMF equation of the transformer. What was the EMF equation? So it is 4.44. And the flux is maximum flux. Please remember, the flux is maximum flux multiplied by the number of turns. So if I'm talking about E1, it will be N1. And if I'm talking about E2, all the other quantities will be the same because the frequency is the same for both primary and secondary. The flux is also common to both primary and secondary, and the number of turns is N2. Okay. So now with this, you should be able to calculate definitely what is phi max, right? Because I can say 500 divided by the turns is 400 and frequency is 50 multiplied by 4.44. That is going to give me what is phi max. From which I can calculate phi max divided by 60 multiplied by 10 power minus 4. That will give me what is B max. So this is the area of cross section of the core. Okay, so that is going to be B max. So this is clear. Any questions? So this is going to be your B max. Now what is the secondary voltage? I think that is the next question. Voltage induced in the secondary winding. So voltage induced in the secondary winding. So we have N2 by N1 equal to E2 divided by E1. So I should be able to calculate E2 as N2 divided by N1 multiplied by E1. So this is going to be N2 by N1 is how much? 400 and 1000. So 1000 divided by 400 multiplied by 500. Right? So that is going to be 1250 volts, right? Because 5 by 4 is 1.25. So I'm going to have 1250 volts. Any questions? Induced EMF in the secondary will be proportional to the number of turns in the secondary. Okay. The next one, the required no load ratio. Ratio in a single phase 50 Hertz core type transformer is 6000 by 250. Find the number of turns in each winding if the flux is to be just above 0.06 Weber. So in this particular case, the flux is given to be greater than 0.06 Weber, slightly higher than 0.06 Weber. That is what is given. First thing. Second thing is, it is the voltage ratio, no load ratio of the transformer is 6000 divided by 250 volts. So this is going to be 6000 divided by 250 volts. That is actually the transformer voltage ratio. So this is going to be V1 divided by V2. Okay. And it is a 50 Hertz transformer. So what is being asked is number of turns in the primary and secondary both. Both are being asked. Okay. So if I say 250 volts, 250 is going to be equal to 4.44 F5 multiplied by the number of turns N2. So I can write this as 4.44 multiplied by 50 multiplied by 0.06. It's slightly more than 0.06. It cannot be less. And multiplied by N2. So you can calculate what is N2. So N2 I have calculated it to be 18 turns. Maybe it will come out to be slightly higher than 18, but the flux has to be slightly higher than 0.06. So it can be under or it can be just 18. That is good enough. So this comes out to be 18 turns. If N2 is 18 turns, then I'm going to calculate what is N1. N1 I can calculate it to be 18 multiplied by 6000 divided by 250. This will give me exactly whatever is the number of turns in the primary winding. I can do it the other way around also. There is no doubt. But because I'm having the secondary turns as less number of turns, I will have more error if I try to start from primary and come towards secondary. Because I'll get more of fraction in the secondary side. Whereas here it will translate into a whole number. Even if I am having 0.1 or 0.2 coming out as the number of turns in the secondary, in the primary side it will be multiplied by 10-fold or 15-fold, whatever. So that is the reason why I have started with the secondary side, which is having lower number of turns, then going towards higher number of turns. So I think this comes out to be 432 turns. Okay. Any questions on this? So the voltage equation of a transformer is a very, very important thing in general. Okay. The next problem, a single phase 6600 by 400 volts 50 hertz transformer has EMF per turn as 15 volts. So E equal to 4.44 F 5 max is EMF per turn. When you multiply that by N1, you get primary voltage. When you multiply that by N2, you get the secondary voltage. So EMF per turn is given as 15 volts. The maximum flux density in the core is 1.5 Tesla. Find suitable number of primary and secondary turns and also the core cross-sectional area. So one thing you have to understand is once you are given the voltage per turn, so voltage per turn is given as 15 volts, which is equal to 4.44 F multiplied by 5 max. From which you should be able to get definitely what is 5 max. And if you are given B max, I can say 5 max divided by B max is the area, cross-sectional area of the core. Okay? B max is given, so you should be able to calculate this without any difficulty. And similarly, primary voltage is given and secondary voltage is also given. So I should say primary voltage is given as 6600 and this is given as 400. So this is given and this is also given. So I can say N1 equal to 6600 divided by 15. Similarly, secondary voltage is given as 400. So 400 divided by 15. Please round it off to closest bigger integer. Always round it off to the bigger integer, not the smaller one. Okay. So this is going to be the number of turns in the primary and secondary. Okay. So let's try to look at problem number 6. The primary winding of a single phase transformer is connected to a 230 volt 50 hertz supply. The secondary winding has 1500 turns. The maximum value of core flux is given. Determine the number of turns in the primary winding, secondary induced EMF cross-sectional area of the core if the flux density is so and so. So again, you are given a voltage, you are given the core flux, you are given the frequency. So you should be able to find the number of turns, right? 230 volts is given, 50 hertz is given, flux, maximum value of flux is given. So you should be able to get definitely. So in problem number 6, you are given 230 volts, which is equal to 4.44 multiplied by frequency 5 max and N1. So you are already given F, you are given 5 max. So you should be able to get what is N1 without any difficulty. And if you have N1 and N2, you can say N1 divided by N2 equal to V1 divided by V2, which is actually 230 volts divided by V2. So you should be able to get what is V2 because N2 is given as 1500 and N1 is already calculated from here. So you should be able to get what is V2. Okay, fine. And I think the last one that is being asked is 5 max is already given. I think flux density is given. You are being asked for the cross-sectional area or vice versa. So that also you should be able to do. So 5 max divided by A is equal to B max. So if I am given two of these quantities, either this and this, then I should be able to calculate this. Okay. Problem number 7. A 50 kVA single phase 50 Hertz transformer has a turns ratio of 300 by 20. The primary winding is supplied with 2200 volts. Calculate the secondary induced EMF, rated currents of primary and secondary, and maximum value of flux. So 50 kVA is given and turns ratio is given and the primary winding is supplied with 2200 volts. So 2200 volts is primary voltage and 50 kVA is the transformer rating. I should not even say power rating, it is apparent power rating. It is volt ampere rating. So I should be able to write this as volt ampere rating. And the turns ratio is given as 300 by 20. So I can calculate definitely what is the secondary side voltage. That will be 2200 divided by 300 multiplied by 20. This will be V2. This will be the secondary voltage. Right? So it's a step down transformer. Primary side voltage is 2200. Secondary side voltage is going to be much smaller. So it's a step down transformer. And what are the current ratings? Current rating of the primary, how much is it? How will you calculate? Volt ampere rating is given. So how will you calculate ampere? Volt ampere rating is given to be 50,000. So if you divide by voltage, you should be able to get the current. So what is the voltage here? Current rating of the primary, how much is the voltage of the primary? 2200. So this is 2200. Similarly, if I want the current rating of the secondary, what should I do? Yeah. Yeah, you can use the turns ratio. So how will you do that? If I call this as I1, if I want I2, what should I do? I2 equal to N1, N2. I1 multiplied by N1 divided by N2. Okay, fine. And finally, flux density is asked, which you can calculate. Flux or flux density, I don't think it's a big deal because you are going to write this as 4.44 F phi max multiplied by N1. Right, from which you can calculate what is this phi max value. Okay, any questions? Eighth question. The following data is given for a single phase 50 Hz transformer. B max is given 1.41 Tesla. Area of cross section of the core is given as 0.01 meter square. Current density in the conductors, the primary and secondary winding conductors, is 2.5 mega ampere per meter square. Conductor diameter is 2 millimeter. Primary side supply is 200 volt RMS. Calculate the kVA rating of the transformer and the number of turns in the primary. So let me first of all write down the data. So it is said that B max is 1.41 Tesla. So B max is 1.41 Tesla. And area of cross section of the core is 0.01 meter square. So definitely we should be able to calculate what is phi max, which is B max multiplied by A. You should be able to calculate that. So that is essentially 0.01 multiplied by 1.41. So I'm going to have 0.0141 Tesla. Weber. This is going to be, this is the Weber flux. Now what is asked next is, current density in the conductors is 2.5 mega ampere per meter square. So current density generally is indicated by J. I am using the same symbol in general. So this is current density is equal to 2.5 mega ampere. So 2.5 into 10 power 6 ampere per meter square. Okay. Conductor diameter is 2 millimeter. So conductor dia is 2 millimeter. So I can say conductor cross sectional area is how much? This is 1 millimeter is the radius. So pi r square. So pi multiplied by 1 multiplied by 10 power minus 6. So this is going to be the area in meter square. So I should be able to calculate the current in the conductors will be 2.5 multiplied by 10 power 6 multiplied by pi multiplied by 10 power minus 6 ampere. So that is 2.5 multiplied by pi ampere. Right? Now from here, I should be able to calculate what is being asked. Primary supply voltage is given. So you should be able to calculate. The primary current is known. Primary supply voltage is 200 volts. So current multiplied by voltage will be the kVA rating. So I should be able to calculate the kVA rating. So I can write the kVA rating will be equal to V1 multiplied by I1. So this is I1. So I should say 200 multiplied by 2.5 multiplied by pi. This should be the divided by 1000 if I say that is kVA rating. Otherwise it will be VA rating. Right? Volt ampere divided by 1000 is kVA rating. What else is asked? Number of turns in the primary. Straightforward, right? Because you can directly write number of turns. So again I can say E equal to 4.44 F5 multiplied by number of turns. So if I'm talking about E1, this is N1. So I can say N1 equal to 200 volts divided by 4.44 multiplied by 50 multiplied by whatever is the flux we have calculated. So flux we calculated as 0.0141. So I can write here as 0.0141. This will give me the number of turns in the primary. Okay. So we had been looking at transformers, and in the last class, what we did was to look at the transformer on no load. And after that, we also looked at transformer on load. What happens when you connect a load on the secondary side? We looked at that as well. And what we said during the load operation was that we neglected basically core losses. So we neglected core losses and we neglected resistance of the winding. That's what we did in the last class. Okay, so both primary and secondary winding resistances we neglected. These were neglected when we were discussing this in the last class. So what we are going to do now is to consider those things also. Whatever we neglected, we want to consider those things as well. Last class, what we actually looked at was the leakage. If we have a leakage reactance of the transformer, or leakage flux of the transformer, how do we account for it? So that we said basically that you have to take whatever is the winding. Along with that, we were taking a reactance in series, and the reactances we called as the leakage reactance. So this is X1. So this is X1, let's say. And you are going to have this as X2, and X2 is the leakage reactance of the secondary winding, and X1 is the leakage reactance of the primary winding, and I am indicating the core by these two lines. Whatever two lines I am indicating, that is iron core that is being indicated. And we said that we are applying a voltage V1 and we are getting an induced EMF E1. And E1 and E2, if you look at the turns ratio, you can say E1 by E2 is equal to N1 by N2. But if there is some portion of the flux which is really not linking with the other member, that is the primary flux is not linking with the secondary, or secondary flux not linking with the primary, that portion we call as the leakage flux. That's what we said as leakage flux. And we said that whatever is the flux that is linking both these things, the primary and secondary, we call that as mutual flux. So this is mutual flux, whereas these are going to be indicative of leakage flux. And the leakage flux drop whatever is the additional voltage which is only corresponding to one member of primary or secondary, we call that as the leakage reactance drop. So we indicated that with X1 in the primary side and X2 on the secondary side. And we basically said that after this drop, whatever is left over here will be V2, which is actually the secondary terminal voltage or the load voltage. What is actually available for the load is after the drop in the leakage reactance. That's what we said. And we also looked at methods of reducing leakage. We saw that as well, methods of reducing leakage. So in the methods of reducing leakage, we said a few things. I'm just reiterating whatever we said in the last class. The first and foremost thing we said was, if we have actually rather than core type construction, which is actually consisting of two limbs like this, and we just put the primary on one side and secondary on the other side. So this is generally called as core type construction. Rather than having core type construction, I can try to have shell type construction. So in shell type construction, what we would see is, if this is the entire core, which is going to be made up of iron, I'm going to have actually the central limb is the only one which is going to have the windings. So I'm going to have the primary here like this, and the secondary just beneath that I may have another winding. So I will have primary here with N1 turns and secondary here with N2 turns, and all around you will have iron, because of which the leakage is going to be really. So this is shell type construction. So the shell type construction is going to definitely reduce the leakage because the entire winding is surrounded by iron on all the other sides, and that is the reason why it will not go through only the air path, which is actually the leakage path. So the leakage is going to be minimized tremendously when you use shell type construction. The second thing we said was concentric windings, that is primary and secondary will be wound around each other. So low voltage winding will be inner side and high voltage winding will be on the outer side. So it could be concentric winding or it can be sandwiched winding. So either of these two can definitely make the leakage reduce tremendously. The third one we said was to make the windows long and thin. So you are going to look at this particular, this is called window. This is the window. So this window will become as thin as possible and as long as possible. So the limbs will be pretty long. That's what we are trying to say. So these two portions are generally known as limb. This is one limb and this is another limb. Whereas we call this portion as yoke and this portion is also yoke. So the yoke portions will be small as possible. The width of the window will be very small, whereas it's going to be thin and long. That's what we tend to do if we want to reduce the leakage. Okay. Now that we have looked at the leakage reactance and we have looked at what happens to the transformer on load when you are not considering the core losses or when you are not considering the resistance of the winding, let's try to now look at all these factors which we have neglected earlier and try to put it together in the form of overall transformer representation. So let me call this as complete equivalent circuit of the transformer. So this is the complete equivalent circuit of the transformer that we are going to develop. Okay. So let me again draw ideally, you know, maybe just a representation transformer. So this is my transformer, which is in core type construction. And I'm going to have the primary winding probably like this. And I'm going to have the secondary winding somewhat like this. So I have primary and secondary on either side. And I'm going to apply a voltage V1 here. So this is V1. And I'm going to take out a voltage V2 here. So what is available at the terminal I call as V2. Okay. And in all probability, I would like to connect a load here because transformer, I will not have it just for the heck of it. I would like to supply some load. So obviously, I'm going to connect a load on the other side. So this is what is my load. Let me call this as some ZL. Load impedance. It can be resistive, it can be inductive, it can be resistive and inductive together. So this is load impedance of the transformer. Okay. So now I'm going to first of all show the primary winding on this side. I'm drawing the equivalent circuit slowly. So I'm going to show the primary winding on this side and secondary winding on this side with the core sitting in between. And let's say the primary induced EMF is E1. And let's say the secondary induced EMF is E2. What I am applying on this side is V1. Okay, this is an alternating voltage what I am applying. Now obviously, even when initially there is no load connected on the secondary side, the transformer is drawing a very, very minimum current. I told you it will be generally less than 5%. Okay, so it is drawing a very, very minimum current. Less than 5% means I'm talking about 5% of rated current. Okay, so this is going to be the no load current. Okay, under no load condition, this is going to draw a current which is actually less than 5% of rated current. However, this winding will have its own resistance. So let me show some resistance here. The resistance drop may be really, really minimal because of two reasons. One is the resistance of the transformer winding itself will be very small because it's a copper winding. And generally, it will be a thick copper winding if I'm talking about a high capacity transformer. Okay. So I'm going to have very, very minimal amount of resistance. That's one thing. And second thing is I'm going to have only 5% of rated current. I'm saying during the no load condition. So the drop is going to be really, really minimal under no load condition. But I don't want to completely neglect it. That is the reason why I'm showing this resistance. So let me call this as R1. And this R1 is primary winding resistance. This is going to be the primary winding resistance. Similarly, I should have a secondary winding resistance also if secondary is carrying a current. If secondary is not connected to any load, the resistance will not matter because that will also not carry any current. But in case I'm considering some load connected across the transformer, I have to take a secondary winding resistance. Let me call that as R2. So let me write R2 as secondary winding resistance. So this is going to be the secondary winding resistance. Okay. Now, apart from this, I definitely have to connect the leakage reactance, which we already talked about, because you cannot eliminate it 100%. So you are going to have certain amount of leakage reactance for the primary. The same way I should have some leakage reactance for the secondary as well. So I'm going to show X1 here and X2 here. Now I'm going to connect the load after this. So here is where my load is. So the load is ZL, what I have connected. And I'm going to connect here also, complete the circuit here. So this is the overall equivalent circuit I can draw for the transformer. If I'm not considering as yet XM and whatever is the core loss component. That I have not accounted for still. Okay. So if I have to account for that, I should in fact show it as though there is a reactance by name Xm here. Xm is actually the mutual inductance, if I may call the mutual inductance between these two as Lm. That is, whatever is the current that is flowing here, that is going to induce an EMF here. And whatever is the current that is flowing here, that is going to induce an EMF here. So when I try to look at what is I1, rather whatever is the primary current, that is dI1 divided by dt multiplied by Lm. Lm is the mutual inductance existing between the primary and secondary. That will give me what is E2. The same way I'm going to write Lm multiplied by dI2 by dt. If I try to write it in terms of inductance and current, I have to write it like this. That will be E1. So I'm looking at how these two are coupled because of the inductance or the flux existing between them. So this Lm is the root cause for transformer action. What is causing really the primary and secondary to be linked with each other? They are linked with each other not electrically but magnetically. And magnetically they are linked with each other because there is a common flux factor between the primary and secondary. That's the only reason why you are getting this induced EMF. So I should say Lm, when I look at it, initially E2 is induced only because of whatever is the current that is drawn by the primary. There is no secondary current at all. And the primary induced EMF is because of its own flux. There is nothing coming from secondary. Okay. So I should say that this is causing really the mutual induction between the primary and secondary. So what I should show here is some Xm value, which is actually the root cause for the transformer action itself, which is common to both primary and secondary. Apart from that, I should definitely show one more factor which is corresponding to the core loss, because the core loss is real. It is going to happen no matter what. I can try to reduce it by lamination. I can try to reduce it by adjusting the material property in such a way that the BH loop is small, but I cannot eliminate it completely. So I should show generally a core loss resistance, which is a fictitious resistance. I will not be able to measure it. I cannot put a multimeter or something and measure the resistance of the core and say that is what is core loss resistance. Not at all. This is essentially representing the losses that are incurred inside the core. Okay. So let me call this as RC, which is the core loss component of resistance, which is a fictitious resistance. So if I now draw the transformer equivalent circuit without showing the core at all, I should show it this way, that this is R1, this is X1, and I'm going to have RC, and I'm going to have Xm, and I'm going to show this completely connected to V1. Okay. And on the other side, I should show the secondary winding. This Xm is between these two. Okay. And I'm going to show this as E2. Voltage induced is E2, whereas voltage induced here is E1. And I'm going to have R2, and I'm going to have X2, and of course the load impedance, which is ZL. So this is essentially representing the complete equivalent circuit of the transformer. One question I would like to ask you is, why should I put RC in parallel with Xm? Why not in series? It is essentially working on the same voltage. See, the entire core loss is because of the flux. And the flux is proportional to V by F ratio. We just saw it in the transformer equation. So as long as you are operating the transformer at a particular frequency and you are applying rated voltage, the flux is going to be at rated value, no matter what. Okay. So if the flux is at rated value, the flux causes the iron loss current. So the iron loss in the core. So the iron loss or core loss, okay, that is going to be essentially caused because of the voltage, not because of the current. The current does not matter. The core loss depends upon what is the voltage to frequency ratio. Voltage mainly causes the core loss. So if I talk about what is the initial no load current, so I can say the current that is flowing here, if I say this is Im, this current is magnetizing current, which is actually establishing the flux. Im will be equal to V by Xm. The same way we are going to say core loss, which is generally proportional to about B square or B power 1.8. That's what they say normally. Okay, it is an empirical relationship. It is not really derived theoretically, it is derived experimentally. That is the reason why we call that as empirical relationship. Core loss is roughly proportional to B square. Because of which we normally say V is proportional to voltage. So we are going to say that, or rather voltage to frequency ratio or voltage in general, if I am keeping the frequency as a constant. So I should definitely have this particular current, if I may call this as IC. So IC is going to be again V divided by RC. Both of them are applied with the same voltage, and IC plus Im together, that is what is going to give me the no load current. So if I call this as I0, I0 is essentially going to have IC and Im together. So I should write I0, which is the no load current, that is going to be equal to IC plus Im. And both of them are applied with the same voltage. That is the reason why they have come in parallel. So this gives me the complete equivalent circuit of the transformer, where I have taken care of the core losses, the magnetizing current, and the resistances of the winding as well. If I'm going to have a current I2 here, I will definitely have a reflected current which is flowing through this winding, so that I'm going to nullify whatever opposition I'm getting from the secondary side. The secondary is going to establish a flux which will oppose the original flux. So that opposition has to be completely nullified. For nullifying that, I will require something called probably I1 dash, I can say. Some books write this as I1 dash, some books write this as I2 dash. That is the reflected current from the secondary side. Okay, so now I will have I2 dash plus I0. All of them are vectors. That is going to be I1, what is drawn by the transformer. So I2 dash is mainly the reflected current from the secondary, and I0 is the no load current which was required initially to establish the flux and fend for the core losses. So when I add all of them put together, I will get I1. So I should be able to write this as I2 dash plus IC plus Im. All of them put together. All three of them put together is going to give me what is known as the primary current I1. Now after all, when I am applying KCL or KVL for this kind of a circuit, then I have to apply a KCL separately for primary and KCL separately for secondary. I don't want to do that. So if I can somehow club both of them, it will be very good. So how to club the primary side and secondary side together? So to club them together, if I say that E1 by E2 equal to N1 by N2, that's what we said earlier also. E1 by E2 is equal to N1 by N2. And after all, if the voltage is stepped up, the current is stepped down. And if the current is stepped up, the voltage is stepped down. So the power is invariant. Whether I look at it from the primary side or secondary side, the power will be invariant, absolutely. Okay. So if I say that the loss that happens here is I2 square R2. And if I want to represent this R2 from the primary side as R2 dash, I want to represent this by an equivalent resistance on the primary side. And power loss should not change. Okay. So in which case, I have to write this as I2 square R2 should be equal to some R2 dash multiplied by I1 square. Because I'm neglecting the no load current. No load current is so small that I can afford to neglect it. Engineering is all about approximation. Generally, you don't behave like mathematicians. You tend to approximate a lot of things. Only thing is, ultimately, when you look at the behavior should be very similar to what you see, pragmatically or practically. So the approximation cannot be done arbitrarily. So this is going to be, you can say R2 dash from here. What is equivalent? That is seen from the primary side. The secondary resistance seen equivalently from the primary side. That will be equal to I2 divided by I1 the whole square multiplied by, right, R2. R2 is the actual physical resistance of the secondary winding. And R2 dash is the equivalent resistance seen from the primary side. But what is the actual secondary winding resistance seen from the primary side? Okay. Now, this I2 by I1, we wrote N1 I1 equal to N2 I2. This was the ampere turn balance we talked about. So I can say very clearly I2 divided by I1 equal to N1 divided by N2. So I can just substitute that here. This particular expression I should be able to substitute here. So I can simply say this is N1 divided by N2 the whole square multiplied by R2. So I should be able to migrate the secondary quantities to the primary side or the primary quantities to the secondary side as and when I require to do so. Now what I can draw as the equivalent circuit will be, this side I have R1, I have X1, I have of course XM, and I have RC. So XM is the magnetizing reactance, which is the mutual inductance between the primary and secondary. And the mutual is generally very, very large in a transformer because you have iron core. Most of the flux is going to confine itself to the iron core. Hardly there will be any leakage, and you tend to reduce the leakage also by various means, right? By adopting various procedures. So if the leakage is reduced quite a bit, I'm going to have XM to be a large value. This will be a large value. Whereas this will be a small value. Again, large and small are relative. To tell you, this leakage will be only about 5% of XM or less than 5% of XM. In fact, X1 plus X2 both put together will be less than 5% of XM. Generally in a good transformer. If you deliberately design a bad transformer, it's different. Okay, I can always make more air gap and then, allow a lot of flux to leak. But that is not the point. If I want really a good transformer, good working transformer, then I have to minimize the leakage. Okay, so now I'm going to have on the other side, I have to write X2 dash, which will be just like how real power is invariant, reactive power will also be invariant. So I should be able to write the same thing, which is actually N1 divided by N2 whole square multiplied by X2. Okay. Now I'm going to have the other one, which is R2 dash. And R2 dash, we have already written the expression, so I am not rewriting it. So this is the expression for R2 R2 dash. Okay. And I'm going to have now the load connected on the other side. The load also, I cannot write ZL anymore. I have to write this as ZL dash because I have transferred everything to the primary. Okay. So I'm going to see that this is the equivalent circuit I have for the transformer, and this is I0. What is going here is I0, and this is going to be I2 dash, which means I'm going to have I1 here, which is summation of I0 and I2 dash. And of course, I'm going to give V1 here. Okay. And I will get, of course, normally V2 here. I'm going to write that as V2 dash. Again, shifted to the other side, and V2 dash is going to be N1 divided by N2 multiplied by V2. Right? For voltages and currents, we have to use only N1 by N2 or N2 by N1, whereas when we are using it for power or reactive power, we have to use it as the square of that because the current is also squared there. That's the reason. Okay. So this is going to be the overall equivalent circuit of the transformer. Now considering this, let us try to draw the phasor diagram for this transformer with the entire equivalent circuit. Again, I am going to start with the common quantity, which is flux. So this is the flux, which is common to both primary and secondary. And I will have a magnetizing current, which is actually causing this flux. So this is going to be IM. And magnetizing current is an inductive current, so it should lag behind the voltage by 90 degrees. So I have to definitely consider the voltage here. This is going to be the voltage, which I may call as V1. So this has to be 90 degrees. Between these two, I will have 90 degrees. So I'm going to have the core loss component of current, which is again drawn by RC, which is fending for the core losses that are incurred in the iron core. So let me call this as IC. So when I add these two together, I will have this as I0. So this is the no load current of the transformer. Okay. Let me try to show E2, E1, both of them almost equal to each other, assuming turns ratio is 1. Okay. So I'm going to have this side. This is going to be E2 or E1, either of them. Now what I get as the current that is flowing through the secondary side or the load, let me call that as I2 dash. I don't know what kind of load I have. It can be resistive, it can be inductive, it can be whatever, doesn't matter. But let me just arbitrarily take some value of current. Maybe this is I2. I'm just taking this as I2. I2 dash rather. Okay. Or I2 itself doesn't matter because turns ratio I have assumed it to be 1 right now. So that is I2 dash or I2. So when I try to draw it on the primary side, I should show it as though it is the reflected current. I'm just showing it on the other side so that I'll be able to add it with I0 very easily. That's the reason. Okay. So this is, let us say, I2 dash, whereas this is, let us say, I2. Let me show this as I2. Now, one thing I have to do is, I have on the secondary side, R2 dash and X2 dash. So I2 dash multiplied by R2 dash plus JX2 dash. That will be the drop what is taking place in these two elements. That has to be added to V2 dash to ultimately arrive at what is E2 dash. If I may call this as E2 dash, that will be same as E1. Both of them are one and the same. Okay. So I should say E2 dash will be equal to V2 dash plus I2 dash multiplied by R2 dash plus JX2 dash. Okay. Is that clear? So I can first of all look at what is V2 dash from here. I don't even know what V2 dash is. So if this is I2 dash, let me first of all write I2 dash R2 dash will be in phase with this exactly. Okay. Now I have to find out where I2 dash JX2 dash will be. Right. In what direction will it be? It should be 90 degrees leading. It should be 90 degrees leading. So if it has to be 90 degrees leading, I have to draw it somewhat like this. This is how it will be. Right? I2 dash X2 dash will be somewhat like this. So let me draw it parallelly. So this becomes I2 dash JX2 dash. This is I2 dash R2 dash. Okay? Might erase the whole thing. Okay. So let me add these two. This gives me what is the drop in R2 dash plus JX2 dash. So what is this value? This is going to be I2 dash multiplied by R2 dash plus JX2 dash. That is the value. Okay. Now I told you here when we wrote the equation, E2 dash minus this will give me V2 dash. So I have to subtract this. So this is the vector I have. So I have to draw a vector exactly in the opposite sense but parallel. Oh. So this is I2 dash. And I'm going to draw a vector exactly parallel to this but in the opposite sense. So this is actually minus I2 dash multiplied by R2 dash plus JX2 dash. So when I subtract or add this minus of this to E2 or E1, what I get here, right? This vector is going to be V2. This is V2 now. This vector is going to be V2. This red color, whatever I have drawn, happens to be my V2. So what you look at as V2 is not exactly equal to E2. It is slightly less or after some drop. I can't say less. Depends upon what kind of load I have, how much of current is flowing. All those things are going to matter. So that tells me really E2 and V2 are not equal to each other. But please note I have exaggerated everything here. R2 is generally very small. X2 is very small. So the drop what I have shown is not so high. Generally it will be less than 5%. That's what I told you. So it's a very, very minuscule drop. However, E2 and V2 are not exactly equal to each other. That's what I'm trying to say. Okay. Now I have got this I2 dash. I have got this I0. Let me add to I2, I0. I have to add this I2 dash. So I have to draw an I2 dash which is parallel like this. When I add these two, what I get, that is I0 plus I2 dash put together, what I get, that is actually my I1. So this happens to be my I1. Oh. Just a second. Let me draw this I2 dash as it is. This is I2 dash. So my I1 is going to be somewhat like this. Let me draw it like this. This is I1. I have to just draw these two put together. Okay. So I1 is basically I0 plus I2 dash added together is going to be I1. So doesn't matter if it gets erased. Let me erase this and draw I2 dash here again. And when I add these two together, I am getting some current like this. This is what is I1. So this is I1. Now that I have I1, I can subtract I1 R1 plus I1 JX1 from my V1, which will give me E1. Please remember V1 minus I1 multiplied by R1 plus JX1 will give me E1. Okay. So that will complete the phasor diagram of the transformer. If I take I1 multiplied by R1 and I1 multiplied by JX1, add them together, that will give me the primary drop. So that is going to give me what is the value of E1, induced EMF in the primary. One thing I want you to notice is, if you look at the power factor angle on the secondary side between V2 and I2, it's very, very small. You can see that this is the power factor angle on the secondary side. Whereas if I look at the power factor angle on the primary side, it is definitely enlarged. Between I1 and V1, if I try to look at the power factor angle, this is phi1. The power factor angle definitely on the secondary side is smaller as compared to the primary side. Or I should say power factor of the transformer on the primary side, on the secondary side is better than, is greater than the power factor on the primary side. That is because, first of all, you are adding what is the drop in the secondary winding itself. Then you are also adding the magnetizing current. And then you will be adding the drop in the primary side. All of them put together definitely is going to make the power factor deteriorate pretty badly in a transformer. Okay. So that is essentially causing the power factor on the primary side to deteriorate as compared to the secondary side power factor. So there are two things we consider as the performance parameters of the transformer. One we call as what is the voltage drop within the transformer. How much is the voltage drop? That is, if we say R2 plus JX2 is causing a voltage drop, R1 plus JX1 is causing a voltage drop. What is the kind of voltage drop we have in the transformer? The second thing is efficiency. What are all the power losses in a transformer? So these two are the major performance parameters of the transformer. And those performance parameters we'll look into in the next